Most reactions occur in a sequence of elementary reaction steps. A balanced reaction or overall reaction only tells you what is the reactant and what is the product. It does not tell you what happens at the molecular level. At the molecular level, the reactants may undergo many steps until it forms product, and these steps is called elementary reaction steps. A collection of elementary steps that explains how the overall reaction proceeds is called reaction mechanism. Since elementary steps are the steps happens at the molecular level, we can write rate laws based on elementary steps. Okay, if you have a elementary step involves only one reactant, okay, for this one, ozone is one reactant. The reaction is called unimolecular step, and the reaction should be a first order. Now, if the elementary step involves two reactants, such as this one, NO and O3, then the reaction is called a bimolecular process, and the rate law is a second order. Now, if the elementary step involves three molecules, that's called a trimolecular process, and the rate law is a third order reaction. Since the overall reaction does not tell us what happens at the molecular level, we cannot deduce the overall reaction rate law just by looking at the overall reaction. However, because elementary steps happens at the molecular level, we can write a rate law for each elementary step, and then we can combine them together, give you the overall reaction rate law. In this section, we are going to introduce how we can do that. Let's study a simple reaction mechanism where A goes to B, but B also goes back to A. Now, because these are elementary steps, and therefore we can write a rate law. So for the forward reaction, since the reactants only involve one molecule, A, and that's a unimolecular reaction, and therefore the rate law is first order, so Ka. All right. Now, because A is consumed, and therefore it's negative, that's the differential equation for the forward reaction. Now, what about the reverse reaction? In the reverse reaction, the reaction also involves only one reactant, so it's also a unimolecular reaction, and the rate law is first order. But in this case, it should times concentration of B, because B is the reactants for the reverse reaction. All right. Now, for the reverse reaction, it forms A. So for differential equation for A, it should be positive. Okay. So no negative sign is added to this equation. So what actually changed for A? So this tells you the A will be consumed, and this tells you A will be produced. So the net effect is you add this together. That's the total change for A as a differential equation for this overall reaction. All right. So next slide, we're going to derive integral rate law for this reaction. In the last slide, we show that for a simple reaction mechanism where A goes to B and B also go back to A, the reaction differential equation is like this. All right. Now, in this equation, you have three variables: A change with time, B change with time, and T time is also variable. Three variables. We need to make a modification. Only two variables. All right, and then separate variables we can integrate. Okay, so if we assume at the beginning we only have A, that's the initial concentration, no B, then at any time the concentration of A and the concentration of B that is formed, they add together should equal to the initial concentration of A. Okay, so if we plug in here, then we'll have only two variables. All right, so we'll skip all the steps, and these are the results. and this tells you the concentration of A, okay, as a function of time. All right, so these are the rate constant, forward rate constant, reverse rate constant, initial concentration of A. And this is the concentration of B at any time, and time is here, initial concentration of A. Okay, now we're going to plot this in the next slide. In the last slide, we showed the integral rate law for a simple reaction mechanism where A goes to B, B also go back to A. And this is the concentration of A, the reactants, and as a function of time, and this is the product concentration as a function of time. If we plot them in this concentration versus time, we get this curve for the reactants. So reactants first decrease with time. So reactants is consumed, eventually becomes a constant. The product initially increases with time. So you produce the product, but eventually also becomes a constant. That suggests that when the time becomes long enough, the reaction reaches equilibrium, and these are the equilibrium concentration. Now, equilibrium concentration can be calculated using this integral rate law when we assume the time is infinite. Okay, so when we plug the infinite time, then we get the theoretical concentration at equilibrium, and these are the results. Okay, so if we use the product equilibrium concentration divided by equilibrium concentration, we should get the rate equilibrium constant. Okay, equilibrium constant is the product divided by reactants, and so cancel this concentration and this constant. So we get this equation, and that is the equilibrium constant equals the rate constant of the forward reaction over reverse reaction. Now this is an important equation. It is a equation relates thermodynamics to kinetics. So this capital K is equilibrium constant. It's about the thermodynamics, and the small k is about the kinetics, the rate constant. So forward rate constant divided by reverse rate constant. So in the future, if we know two of them, we can calculate the third one. All right. So sometimes we know the kinetics, we know the forward reaction rate constant, reverse rate constant. Then we also know the equilibrium constant using this equation. So also the equilibrium of the product divided by equilibrium of reactants equals the forward rate constant divided by reverse rate constant. That suggests this cross multiplication also equal, and that gives you this equation. So the forward rate constant times the A, okay, reactants at equilibrium equals the reverse rate constant times the B at equilibrium. Now, if you look at it closely, this is just the reaction rate for the forward reaction. Okay, it's the K rate constant times reactants. So that's the forward rate constant. So a reaction rate of forward, and this is the reverse rate constant times the B at equilibrium, and that's the reaction rate when the reaction reverse reaction when the reaction reaches equilibrium. So this equation suggests that at equilibrium, the reaction does not stop. Okay, it still proceeds, but the forward reaction rate equals reverse reaction rate. Okay, so this leads to an important conclusion that at equilibrium, the reaction is still proceed. All right, it's called dynamic equilibrium. All right, forward reaction rate equals reaction rate. That's when the reaction reaches equilibrium. In the last slide, we studied simple reaction mechanism where A goes to B, B also goes to A. And for the forward reaction rate constant is K, reverse is K prime. At equilibrium, the reaction rate for the forward reaction should equal to the reaction rate for the reverse, or K times A at equilibrium equals K prime times B. And from that, we can show that the equilibrium constant equals the rate constant for the forward reaction divided by reverse rate constant. Okay, so that's what we get from this simple reaction mechanism. What if the forward reaction involves two molecules, a bimolecular process? All right, so that's a second order reaction. Now the conclusions are similar. When the reaction reaches equilibrium, the forward reaction rate should still equal to the reverse reaction rate. That's when the reaction reaches equilibrium. But in this case, the forward reaction rate is a second order, so it's Kf times A times B, and the reverse is reverse K constant times C. Okay, and what is the equilibrium constant? Now the equilibrium constant should be the product divided by reactants, but formally the concentration should divide by a unit because K is a dimensionless. So in order for this to dimensionless, each concentration should divide by a unit. All right. So the product only divided by once, but the reactants twice because you have A and B. It's a second order. All right. And therefore, you cancel once. So this cancel once. You still have one unit. All right. And then the rest will be product divided by reactants. Now from this equation, we can find that the product divided by reactants should equals to the rate constant of the forward reaction rate constant divided by reverse rate constant. That's exactly the same as we find out from the simple reaction mechanism. So the equilibrium constant is still the rate constant of the forward divided by reverse, but then you have to times a unit if the forward reaction is a second order, so that K is dimensionless. Okay. One way to measure the rate constant, forward and reverse rate constants, is use Perturbation-Relaxation Method. In this method, we let the reaction reach equilibrium at a certain temperature, T1, and then we let temperature suddenly jump to another temperature, let's say T2, and the reaction will eventually reach a new equilibrium. Okay, but it takes time to reach this equilibrium. So note that at T1, the rate constant is Ka, Kb, and at the new temperature T2, the rate constant change to Ka prime, Kb prime, and A equilibrium, that's the new equilibrium concentration for A, and this is new equilibrium concentration for B. And this is a plot, shows initially the reaction reaches equilibrium at T1, and when temperature goes to T2, the reaction will eventually reach a new equilibrium, and that's the new equilibrium concentration, and it takes time. So the goal of this experiment is to measure this time, and in theory, we'll derive equation to relate this time to the rate constant, so we can calculate the rate constant. So to do that, we first define x. So x is tells you how far away the concentration is from the new equilibrium concentration. A is the concentration at any time. Suppose at this time you have A, and the x tells you the difference of this concentration from the new equilibrium concentration. Now using this x, we can calculate the concentration of A and the concentration of B at any time. All right, x naught is the difference between the equilibrium concentration of T1 and the equilibrium concentration of at T2. Okay, so by using x, we now change two variables A, B into one variable, just x. So now let's write the differential equation for A. So for A, remember the reaction has two elementary steps, forward, reverse. Reverse reaction produce A, so it's positive, increase A concentration. So Ka prime, the rate constant, times concentration of B, minus forward reaction, because forward reaction consumes A, so it's negative minus Ka prime forward rate constant times A. Now plug in this concentration, so we have this equation. All right, so this is the A, this is the B. All right, then we expand this equation, so A Ka prime times A equilibrium, Ka prime times X, same thing is here, and then we have this equation. Okay, now note that in this equation, Ka prime times A at equilibrium, that's just the forward reaction rate at new equilibrium. So this is the reaction rate forward at equilibrium. And Kb prime, that's the reverse rate constant, times B at equilibrium, that's the reverse reaction at equilibrium. Now at equilibrium, these two reaction rate, forward and reverse, should equal, and therefore this will cancel each other because you have a negative sign here, right? So it cancel each other. So what we get now is just the negative, the sum of the two rate constant times X. Now note that A equals equilibrium concentration plus X. X is a variable. So when you derivative of A over T, it's just the derivative of X over T. So you get dx over dt. All right, so we have an equation that is dx over dt equals negative Ka prime plus Kb prime times X. All right, we're going to derive the equation relates the time with the K constant in the next slide. In the last slide, we derived this differential equation. In this equation, X tells us how far away the concentration from the new equilibrium concentration. And this equation reminds us a first order reaction. A first order reaction differential equation is negative dA over dt equals Ka. Okay, that's the first order reaction. And in this equation, A can be replaced by X, all right, and the K is replaced by the sum of forward and reverse rate constant. So the integral rate law we derived for this first order reaction should directly apply to this equation. For example, in first order reaction, the concentration A is initial concentration times e to the negative kt, and therefore we can write X equals X naught, initial X naught, times e to the negative, the sum of the 2k times t. Also, for first order reaction, ln A over A naught should equal to negative kt, and therefore we can calculate the t by the natural log divided by 1 over k. Okay, negative 1 over k. That's the t. Same thing is here. Time can be calculated by negative 1 over the sum of the 2k constant times ln x over x naught. All right. So now we are ready to define relaxation time. So what is relaxation time? For simplicity, let's let x over x naught equals 1 over e. Okay, because this will make ln 1 over e just negative 1. So negative negative becomes positive. So the time will just be 1 over Ka prime plus Kb prime. That's called relaxation time. But what does this mean? X divided by x naught equals 1 over e. Well, x will be x naught divided by e. Okay, that will make x equals x naught divided by e. Now remember, in first order reaction, we assume we defined half-life. So half-life is the time to make concentration A equals initial concentration divided by 2. Okay, you consume half of it. That's the half-life. Similarly, here the relaxation time is the time to take to change x becomes 1 over e of this initial x naught. Okay, so in the diagram, it's the time. Okay, it's the time to make x becomes x naught over e. Okay, 1 over e. Now half-life can be measured. experimentally. Similarly, this relaxation time can also be measured. So whenever we measure the relaxation time, then we can use this equation to find out the sum of the two rate constants. Now, if we have the equilibrium constant, then we know equilibrium constant equals the forward rate constant divided by reverse rate constant. So combine these two equations, then we can calculate the rate constant for forward and reverse reaction rate. We have studied a simple reaction mechanism where A goes to B, B also go back to A, and our study show the reaction is dynamic. When the reaction reaches equilibrium, the reaction forward rate equals reverse rate, and the equilibrium constant equals forward rate constant divided by reverse rate constant. So now let's start another simple mechanism called the consecutive reaction mechanism. In this mechanism, the reactants first go through an intermediate I and then goes to the product. So the first step, rate constant is Ka, and the second rate constant is Kb. So to calculate the concentration of product P, we look at the reaction involves P, which is only a second step. And in this step, intermediate I is the reactants. So we can write reaction rate law, which equals Kb times I, because I is the reactant. And we can write a differential equation that is dP dt equals Kb times I. So dP dt shows the concentration of P change, increase. So because produce P, so increase. Now in this equation you have three variables, P, T, I. All right, so we need I to calculate the P. So next we are writing the differential equation for I so that we can integrate. Now for I, you have two reactions that involve this I. One is the second step, which is consumes I. The other is first step, it produces I. So we have two equations. For the first step, because the produce I is positive and the reactant is A, so it's Ka times A. The second step consumes I, so it's negative. It consumes, it reduces, concentration I is reduced by the second step. And the reactance is I, so negative Kb times I. All right, I is the reactance for the second step. So the total I change, you combine together. All right, so it's Ka, okay, that's the first step, which produce I, minus Kbi, which consumes I. Now, in order to integrate this equation, we need to know the concentration of A. A is consumed only on the first step, and first step is a first order reaction, and therefore we know the equation, which is the first order reaction. A is the initial A naught times e to the negative kt. So plug in here, then we only have two variables we can integrate, which we'll show in the next slide. In the last slide, we introduced this consecutive reaction, and we want to calculate the concentration of P, but before we can calculate the P, we need to know I. And this is the differential equation for I, which only involves two variables, I and the T. So that can be integrated. So we skip all the mathematics, and here is the result. That's the concentration of I change with time, which involves rate constant Ka, which is the first step, and Kb in the second step. Okay, so now let's plug in the differential equation for P, the product. Okay, so this goes to here, and then we have only two variables, the product concentration and the time. Okay, so plug in and also skip mathematics, and this is the final results, the product concentration as a function of time. Here are the results of the integral rate laws for the consecutive reactions: the reactant, the product, and the intermediate. Now let's plot them as a function of time. For concentration of A, the reactants, we found that it undergoes exponentially decrease with time, and the final product increase with time. But the intermediate, is kind of tricky. It first increase and then decrease. Now this is not surprising because at the beginning you only have A, and A produce I, so it increases with time. But with time, I start to accumulate, and the second step becomes important. It consumes I, and therefore it starts to decrease. And there's a time when the concentration of intermediate becomes maximum. Sometimes for a consecutive reaction, the intermediate I is our desired product, and the product may continue to form byproduct. And so our goal is to stop the reaction at the right time so that the concentration of the product is maximum. So how do you find the time to get the maximum product I? So in calculus, for a function to be maximum, the slope is 0. All right, slope is the derivative. So here is the integral rate law for the I, that function of I. All right, and then we derivative this function and let this to be 0. Okay, so when you derivative this I, constant doesn't change. This doesn't change. You only derivative of these two exponential, which give you these two. All right, and for this to be 0, constant won't be 0, so these two has to be the same. All right, and then you take natural log on both sides. Then you can calculate the time. So here is the result. The time to reach maximum, all right, I equals 1 over Ka minus Kb, ln Ka divided by Kb. So the time to reach maximum I depends on the relative rate constant. All right, relative first rate constant, second rate constant, first, second. We just show that for a consecutive reaction, the intermediate concentration first increase and then decrease, and there's a time to reach maximum concentration I, and the time depends on the relative rate constant Ka, Kb. Okay, so further studies show that when the first step Ka is much greater than Kb, in other words, the first step is fast, second step is slow, then it will first quickly forms a maximum of I and then decrease with time. Now, if the second step is fast, first step is very slow, so Kb is much greater than Ka. In this case, the concentration of I, and it remains very small and almost independent of time. So it's almost constant. And this is when the I intermediate is a very reactive compound, such as a radical. Okay, so we know radical is very reactive. So it's a high energy compound. So the first step is difficult to form a high energy radical. It's a slow step. But whenever radical is formed, it immediately forms product. Okay, because the first step is slow and the second step is fast, and so the concentration must be small, because whenever it formed, it immediately forms product. So it remains small and constant, and that is the basis for the steady state approximation we are going to introduce in the future. Many reactions undergo complicated mechanisms. Deriving rate law involves complex mathematics if possible. So here we are going to introduce some approximations which make it much simpler to derive rate laws. For consecutive reaction, This is the integral rate law for the product P. Suppose the first step is slow. Okay, first step is slow, and therefore Kb is much greater than Ka. Now, if Kb is much greater than Kb, then you can ignore Ka. All right, and also the e to the Kb will be a very large number. And if you have a negative sign, that means you divide by it, and that will be approximately 0. So you can ignore EKB. Okay? And so what you have is this equation right here. And the Kb cancel each other. So eventually what you get is the product only depends on Ka, because Kb all canceled in this equation. All right? That means that the product only depends on the slow step rate constant. It's the slow step determines the product. Okay. On the other hand, if the second step is slow, okay, so then the equation simplify as here. All right, only depends on Kb. So Kb is the second step. That's the slow step. So in both cases, the product only depends on the slow step. So the conclusion is the slowest step in a consecutive reaction is the rate determining step in a mechanism which controls the overall rate of the reaction. Let's study some cases. So in this case, you have a consecutive reaction. The second step is fast, the first step is slow, and the first step will be the rate determining step. Now in this case, the first step is fast, second step is slow, and therefore second step will determine the overall reaction rate, which is a rate determining step. Now in this case, even though the second step is slow, but the product does not have to go through the second step. It can go to another route. That's the third route. And therefore, in this case, there's no rate determining step. The rate determining step is not just the slowest step. It must be slow and be crucial gateway for the formation of the product. Let's introduce the steady state approximation. In a consecutive reaction, we already showed that the intermediate concentration change with time depends on the relative rate constant Ka and Kb. Now, if the first step is a slow step and the second step is very fast, such as a radical, okay, then the concentration of the intermediate remains low but also constant. Okay, it's almost constant. And that is called steady state approximation. In mathematics, we write the reaction rate for I is 0. So V of intermediate is 0. Okay. Now note that not the intermediate concentration is 0, and that's not right. Intermediate concentration is low, but not 0. All right. It is the rate because it doesn't change with time. It's constant. So your derivative of I over time is 0. And this is an important point we are going to use when deriving rate laws. Let's try to derive a rate law using steady state approximation. So here is the overall reaction. 2A forms 3C. Now can we tell if this reaction is second order because there's a 2 here? The answer is no, because the overall reaction only tells you the reactants and the product. It does not tell you what really happened at molecular level. Okay, so suppose here is the mechanism with several elementary steps. So these are what really happened at molecular level. So the first step, A first forms an intermediate B and the product C. And then the intermediate combined with another A forms 3C. Okay. Now, if you combine these two together, and you will find that the intermediate cancel each other. So one is reactants, one is product. So cancel each other. You get a 2A, 3C. That's the overall reaction. All right. But this is what happens at molecular level. Okay, so we can write the rate law for each of them, all right, and then we combine together, give you the overall rate law. Now, because they are elementary steps, we can write a rate law. The first one involves one molecule, and therefore it's a unimolecular reaction, first order reaction. And the second one has two molecules in the reactants, so it's a second order reaction. It's a bimolecular reaction. All right, so we can write each of the rate law and then combine together. Okay, we'll do it in the next slide. So here is the overall reaction, and this is the mechanism. So our goal is to use the mechanism to derive a rate law for the overall reaction. Now, when we derive the rate law, keep in mind that the final rate law can only contain reactants or sometimes product. It cannot have intermediate, because intermediate is something you cannot measure. All right, you cannot see it. So we can measure reactants, we can measure product, but we don't know intermediate. So it shouldn't be in the overall rate law. Okay, so if it does, if the rate law have intermediate, then that's when you need a steady state approximation or the pre-equilibrium approximation that we are going to introduce later. Using this approximation to express the B in terms of reactants or product. Let's derive rate law for this overall reaction. Okay, now we can choose either a reactants or the product, but not the intermediate. Okay, now after we choose A, for example, then we have to look at the mechanism. Look at the mechanism to derive rate law, not the overall reaction. Okay, so we look at how many steps involves A. So we have first step, second step, both involves A. For the first step, all right, you have forward reaction which consumes A. The forward reaction rate is K, so K1 times A. A is the reactants, so it is consumed. We add a negative sign, all right, that because concentration of A decrease, and so that's how fast it decreases. Now the reverse reaction produce A. So the rate law for the reverse reaction is K minus 1 times the reactants is B and C. Because the reverse reaction is BC are the reactants. So BC times K minus 1. And this produce A, so it should be positive. Okay, so that's the first step, the how A change. Okay, the reverse reaction produce A, the forward reaction consumes A. Now the second step also involves A, but it consumes A. So the forward reaction is K2 times reactants which has A and B. It's a second order reaction. Okay, so you have a negative sign because it consumes A. And therefore the total A change, you combine them together. All right, so that's the first step, reverse reaction, which this is the only step that forms A. And then the first step, forward reaction, consumes A. Second step consumes A. Okay, now is this the end? All right, the answer is no, because in this equation you have intermediate. B is the intermediate. The overall rate law cannot have this, and therefore that's why we need to use the steady state approximation. We'll see in the next slide. In the last slide, we tried to derive rate law in terms of A. However, we found that the equation contains intermediate B, which cannot be included in the rate law. And therefore, in this slide, we are going to use the steady state approximation to find the concentration of B in terms of either reactants or product or both. Okay, to do that, we first write the rate law for B. Okay, and first we look for the reactions that involves B, and they are equation 1 and equation 2. So there are two reactions, both involves B. And in the first step, all right, the B is produced by forward reaction, consumed by the reverse reaction. Okay, so forward reaction rate law is K1 times A. A is the reactants, and produce B, so it's positive. And the reverse reaction consumes B, so it should has a negative sign. And the rate constant is K minus 1. And the reactants for the reverse reaction is B and C. So that's the rate law for the step 1 for B. Okay, how fast the B change. All right, so you have forward reaction produce B, reverse reaction consumes B. Now second step also involves B. It consumes B, so it should be negative K2 times A times B. Okay, these are the reactants in the second step. So the total rate for B, you combine these three together. That's how concentration of B change. Now, what does the steady state approximation say? The steady state approximation says the concentration of B is low, and particularly is constant. Constant means it doesn't change with time. This is 0. This is the change over time. It shouldn't change. That's what the steady state approximation says. Okay, and therefore we let this to be 0. Okay, so this is 0, and therefore we can calculate B. Okay, so just modify this equation. You should easily find the B as a function of reactants and also product in this case. Okay, so finally we get the concentration of B by using steady state approximation without the complex mathematics. And the next step is that we are going to plug in this into the rate law for A and get the final rate law. So here is how we derive the rate law. We first choose reactants A, write the rate law. It turns out that in the rate law we have intermediate, and then we use a steady state approximation to find the intermediate concentration. Plug into this equation, we find the rate law for A in terms of only reactants and the product. Okay, now simplify this equation. So finally, we have the final rate law. Okay, now this rate law is not a first order reaction, nor a second order reaction. It's very common for a complex reaction mechanism give you a complex rate law. However, under special condition, this rate law may become simple. For example, if reactants A has a high concentration and product has a very low concentration, then you can ignore the product and this cancel one, and that give you first order reaction. In other words, at a high concentration of reactants, very low product, the reaction follows first order reaction, and this is called a pseudo first order reaction. So this example tells us that sometimes when we derive rate law, we need a steady state approximation to find intermediate concentration so that the final rate law only involves reactants or products. In summary, for an overall reaction, in order to derive rate law, we have to know the mechanism. Okay, so using mechanism, we can derive rate law either using reactants or product. Now, if the equation involves the intermediate, then we need to use a steady state approximation to find the concentration, and this is the final rate law. Okay, so rate law derived from mechanism, not the overall reaction, and rate law only contains reactants or product, and the intermediate concentration can be obtained using steady state approximation. Here is a question that will be one of your homework. Using steady state approximation to derive rate law for an overall reaction A plus B goes to P, and the mechanism is shown here. This mechanism involves 2 steps, 3 elementary process. Okay, so here is 1 step with forward and reverse, and here is the 2nd step. All right, so you write the rate law for either reactants or product. All right, so in this case, it's more convenient to choose product P. Okay, and then you write the rate law for P. In this case, it should be Kb times reactants I, but I is an intermediate, so it's not acceptable as a final rate law, and therefore that's why you need to use the steady state approximation to find the concentration of B or I intermediate, and then you combine together, write a rate law. All right, so you replace intermediate concentration and find the rate law. So here is the answer. Okay, that's the final answer. The rate law for product, all right, is the first order with A, first order with B. Okay, these are the rate constants. In the last slide, we showed an example of overall reaction A plus B forms P, and the mechanism is shown like here, and we use a steady state approximation to derive rate law as a homework. Now there's another approximation called the pre-equilibrium approximation that is very similar to steady state approximation, but there's some important difference. Now in this approximation, we assume the first step already in equilibrium, and therefore we can write the rate equilibrium constant equals product divided by reactants. Now if we don't have equilibrium constant, then we can write the rate constant for forward over reverse. All right, and immediately we can calculate the intermediate concentration using this equation. So this equals the equilibrium constant times AB, or this ratio times AB. Okay, so we can calculate the intermediate concentration, and then we can derive rate law. So the rate law for P is the 2nd step, which is Kb times I, because I is the reactants. So here is Kb times I, but I is intermediate, shouldn't be in the rate law, and therefore we plug in here the results from pre-equilibrium approximation goes here, and finally we can find the rate law that only involves A and B. Okay, so you see the pre-equilibrium approximation and the steady state approximation, they have the same idea that when we derive rate law, the rate law involves intermediate, and therefore we can use either of this approximation to find the concentration of the intermediate. In pre-equilibrium approximation, we can simply write equilibrium constant and calculate the intermediate concentration. Instead of let the reaction rate of intermediate equal 0, we need to write the rate law for the intermediate. Let this to be 0 and find the concentration of intermediate. Let's compare the two approximations. When you use pre-equilibrium approximation, the rate law is shown here, which is the first order with respect to A, first order with respect to B, and the 2nd order overall. When we use steady state approximation, and this is the result. Again, it's the first order with respect to A and B, and the overall 2nd order. The difference is in steady state approximation, there's additional Kb in the equation. Okay, so when Kb is a very small number compared to Ka prime, then the steady state approximation results go back to the pre-equilibrium approximation. All right, so what does this mean if Ka prime is greater, much greater than Kb? Ka prime is the reverse reaction for the first step. Kb is the 2nd step. So when the Ka prime is much greater than Kb, that will assure the reaction reaches equilibrium. Because if you think about this, Kb is a large number, then the reaction will never reach equilibrium, because whenever you form I not go back to AB, but instead go to the P. So it's not, you cannot reach equilibrium, and therefore you cannot use pre-equilibrium approximation. So pre-equilibrium approximation is valid only when the Ka prime, the reverse reaction for the first step, is much greater than the rate constant for the second step. How do we find the activation energy for a composite reaction with a complex mechanism like this? The pre-equilibrium approximation tells us that the overall rate law is first order with respect to A, first order with respect to B, and the rate constant is the combination of the three small rate constant. So combined together give you the total rate constant. So the total rate constant equals Ka, Kb, Ka prime. Now each of these small rate constant obeys Arrhenius equation, and that is A times e to the negative Ea over Rt. So for Ka, for example, and this is the first forward reaction, it has its own activation energy, so it should be Ea, and you have a own A1. Okay, so for B, you also have its activation energy and a pre-equilibrium, pre-exponential constant. So if we plug in all this into this equation, and that's the total rate constant, and this is for A, and this is for B. Okay, note that you have activation energy for A, activation energy for B, activation energy for the reverse reaction. Okay, now let's combine all this pre-exponential constant together and give a new pre-equilibrium constant here. And the exponential power, when they multiply, the power should add together. So these two add together and minus this one. All right, so they all have RT, so factor out RT, and that give you the activation energy for the first reaction, forward reaction, plus second forward reaction minus first reverse reaction. Okay, now this can be simplified as the new rate, the exponential constant times e to the negative RT over Ea prime. So the whole three combined together give you a new activation energy. And so the new activation energy is just the two forward reaction, first and the second forward reaction, minus the reverse activation energy. Now in this energy diagram, so you have two steps. Okay, this is the reactants, this is the intermediate I. All right, so this is the first forward reaction activation energy, and this is the reverse reaction activation energy. And the second step, this is the forward reaction activation energy. So the total reaction activation energy is these two forward activation energy minus this reverse reaction activation energy. And this is called effective activation energy for the composite reaction. In addition to consecutive reaction mechanism, there are also parallel reaction mechanisms where a reactants may form more than one product at the same time. So we can write differential or rate law for each of these parallel reactions. So this is for the product B, so the rate constant times reactants A, and this is for the second reaction, all right, Kc times A, and for A you have to consume A to form B and C. So for A change, you have two of them, both are negative, they are consuming A. Okay, so the rate constant is Kb plus Kc. So all these can be integrated. All right, so these are the three integrated rate law. This is for concentration of B, this is for concentration of A, and this is for C. Now note that when we write this rate law, we ignore the reverse reaction. Assume ignore reaction is not important. And that means that this reaction is under kinetic control. All right, thermodynamic is not important. No equilibrium constant doesn't play an important role. So only determined by kinetics, and these are the results under kinetic control. Here shows the integral rate law for a parallel reaction. A goes to B and also goes to C with rate constant Kb and Kc. Okay, so if we plot them as a function of time, we can see the reactants A always decrease with time. It's consumed. And for B and C, they are increasing with time. And if we divide B by C, the concentration, then all these terms cancel. And what left is just rate constant of Kb divided by Kc. Okay, so that tells you that under kinetic control, when the reverse reaction is not important, the product ratio is just the rate constant ratio. Okay, the product with the larger rate constant will give you more product, and therefore it's called kinetically favored product. And the yield of a given product is the rate constant towards the desired product divided by the sum of all the rate constant. Here's an example. Under acidic condition, the reactants BP here undergo parallel reaction to form three products, P1, P2, P3, with rate constant K1, K2, K3 given. The question is, what is the yield for P1 formation? Okay. Now, under kinetic control, we show that the yield should be only depends on the rate constant. So it's the K1, which leads to the P1, divided by the sum of the three rate constant. So plug in all the data, and that gives you 0.067. Sometimes in a parallel reaction, the reverse reaction is important. In this case, the reaction reaches equilibrium. And so we can write equilibrium K1 equals B divided by A. We can calculate concentration of B equals K1 times concentration of A at equilibrium. Similarly, we write K2 equals product divided by reactants. So the product C at equilibrium can be calculated by K2 times A. And therefore, the ratio of B over C, the two product ratio, is just the equilibrium constant ratio, K1 divided by K2. So that indicates that if the reverse reaction is important, the reaction is called thermodynamic control, and the product is determined by equilibrium constant. The product with larger equilibrium constant is the thermodynamically favored product. Okay, now let's look at the energy diagram. So if this is the reactants go through a transition state, and then it forms product. Okay, so this is the product. Okay, let's say this is P1. So what determines reaction rate is the energy of transition state, or the activation energy here. So this is the energy determines reaction rate. Okay, so imagine you have another reaction go through a smaller transition state. All right, then this product, let's say this is P2. P2 will be kinetically favored product because it forms faster. It has a smaller activation energy. Now, which one determines equilibrium constant, thermodynamic control? So it's the energy of the product. So for the first reaction, is this energy, delta G, is between reactants and the product here. All right, and this lower the energy, the more stable the product, then the higher equilibrium constant. All right, so for the second reaction, because it has a lower energy, product has a lower energy, so delta G is larger, and therefore P2 is also thermodynamically controlled product. So compare these two reactions, P1, P2. the P2 is both thermodynamic controlled product and the kinetic controlled product because it has a smaller activation energy and also have a lower energy in the product. Okay, now not always this. Now in this case, okay, this energy diagram, the product D, right, the activation energy is smaller. It's the transition state is B. So this is the kinetic control. So kinetic control the product is D. Now what about thermodynamic control? Thermodynamic control is E because E has a lower energy. So delta G is smaller and therefore it forms more E if the reaction under thermodynamic control.